this computer.
Hello.
Hello.
Bonjour, comment ça va?
Ça va,
No.
merci toi?
Oh, sorry.
Ça va très bien.
Super. T'es à Paris toujours?
Non, là, je suis à Buenos Aires.
Ah, ok. D'accord, ouais.
Donc, c'est cool. En vrai, il fait super beau. Donc,
Oh.
ouais, vraiment, ciel bleu. Mm, impec. So let me put just a message on the chat about the session, that we are live and everything. Atoun m'a dit que tu avais un quiz, mais c'est à quelle heure?
Non, mais ça va. Il y a 1 heure. Ça va.
Besides,
Ok.
isn't it 1 hour later?
Pardon? Sorry?
Oh, sorry. I thought your quiz was 1 hour later.
Yeah, I said that.
Oh, okay. Sorry.
So it should
Ok.
not be an issue, yeah.
Okay. Just you will pass first, then.
Uh, oh, yeah, I was first, I guess, already, so
Yeah.
Okay,
Snarks and
nice.
then Starks, yeah. Should not be an issue.
Okay.
Let's
So
wait a few
we
minutes.
will start in 2 minutes.
Yeah.
Of course. That's nice. Hello, everyone.
Just
You still didn't put the link.
Hmm?
Hello. Solen, the link.
What?
By the way, everyone, please check Google Classroom for the attendance and the reading
Oh, yeah.
material. Mhm.
You are a teacher assistant. Wait. Okay. Session 4. No. We are live for the session.
After Monday's session, how are you, people? I know that KZG was too intense, but for me, actually, like my brain still hurts. Oh, Deisha here.
Hi guys, how are you?
Hello, welcome. Good. How are you?
Good.
Wait. Okay, so I put on the chat. Wait, it's still doing.
Perfect.
Rolling. Okay, let me pin it. Boom. All good. Nice. All right. So
I created attendance. Please check Google Classroom. And how are you, Yunus?
Good, thank you. So
Are you
excited to be here. Huh?
We're gonna ask so many questions so that make you feel uncomfortable.
Yeah, hopefully.
Yeah.
This is one of my favorite topics, like in the whole world. So,
Yeah. I
yeah.
constantly hear him about talking Mina. So I'm so excited to listen ZK Snarks here right now.
It was before.
Yeah.
That's not a fair comment.
you're still in Mina or not?
No, let's finish. But still doing some projects, yeah.
Okay, yeah. Yeah, with another 101.
Yeah.
Okay, nice. So normally we will be around like 30, 39 or
Yeah.
30, 50, 40, sorry. Yeah, so they will join the
Yeah,
the
they
chat.
come after like 10 minutes or something like that. Few people come that way. So
Welcome in Web3.
Oh, then I can start.
Yeah, and we are also Gian, who is here, who will lead the second part. So yeah, super excited to have you both here. Normally we have some courses with Melita, but not this time. Alright,
Today
let's
we
go.
talked to instructor Yunus. He's from Node 101 and former Mina, and Gyan. She's from StarkNet Foundation. Today we're going to discuss ZK snarks and ZK starks. So it is going to be awesome, I think. And Yunus, you can start whenever you feel comfortable.
Of course. Hello, everyone. First of all, thank you very much for being here today. I will try doing my best today explaining to you. I have some presentation material, so I'll share my screen. But honestly, I thought this more like a workshop, so please feel free to drop any questions between, or we can continue in a more free way. So this is my presentation. It's not great in terms of color theme, but yeah, I did myself, so
We
not
don't care.
AI. Thank you. So first of all, so today is an introduction to ZK snarks. It's not formal, so meaning that like this is not a fully mathematical introduction. We won't describe how they work mathematically. Apparently, you all here are more developer oriented, so I guess you are looking more into how you can use ZK and how you can I don't know, use it in the best way so that like your application can be stronger. But we are not necessarily trying to understand all of the mathematical foundations. Thus, today is more going to be about, at least my session, more going to be about like how we can use ZK snarks and why they're important and what is the like most important property of a snark, etc. So I hope it will be useful. These are my contacts. Feel free to reach anytime about anything. I don't mind. So first of all, what is a snark? So ZK snark, it's this keywords, and I color coded it. So I hope you won't forget anymore. So ZK is zero knowledge. I guess you already know that, so I won't explain what is zero knowledge. S is succinct, which is today's like main and first topic. N is non-interactive. I guess you already know that, but just as a small reminder, non-interactive means that prover and verifier contacts each other only one time. Prover creates something without talking to the verifier and then sends that, and verifier can verify independently at any time, as many times they wish. So like there is no ongoing interaction. It's not like Diffie-Hellman, for instance. Diffie-Hellman is an interactive protocol. ZK snarks are non-interactive. And ARK stands for argument of knowledge. Probably you didn't hear that before, but basically it's a proof. So like I have a proof that I have some information, and this information is in some specific type. So I already know that you have an introduction to ZK. So like from an example, let's say I have a proof asserting that my input X is bigger than 15. That's a very simple proof example. I have this proof and it takes input X and it asserts that X is being bigger than 15. It can also do like better and more logical stuff. Like it can assert a Merkle witness that my Merkle root is correct. It can assert that, I don't know, I have bigger than 18 years old. This is the classical example of, ZK password, etc. So these are standard stuff that we all know. Today's most important concept to understand is succinctness and what is being succinct. So let's deep dive into succinct and what is succinct. Any questions still here, by the way? Okay. So what is succinct? So, when we say something is succinct, we basically mean that the proof is growing very, very slowly. And what is the proof is growing very, very slowly? This means that the proof size is growing very, very slowly, and the proof's verification time is growing very, very slowly. So that, in respect to what, by the way, in respect to the computation size, meaning that, like, let's say that I am creating a proof, and I am creating a proof for, like, proving my age. Let's say I want to do more. Instead of proving my age, I want to prove my gender and I don't know, my nationality, where do I live, like all of my previous resident addresses. So I want to prove much more. So my computation increased. It says that even if I increase my computation, the proof size and the proof verification type should grow much slower than the actual computation itself. But it's not bounded. So that is very important. Growing very, very slowly, it's important. By the way, mathematically, we say it's like polylogarithmic, meaning that it is much slower than linear, but it is not bounded. And I believe a very beautiful example is this function here, which is 10 to 6 times log n. So as you know, logarithm is not a bounded function, meaning that if I take logarithm of infinity, that is infinity. And I can basically find n as big as giving any logarithm that I wish. Thus, logarithm of something is not bounded either. So log of log n is not bounded either. By the way, everyone here knows what is bounded, right? So
Can you explain in a
Of
few?
course. So I'll show the function. So this is my favorite site. I'm kidding, but it's really good. So let's say log x. So as you see, log x is growing very, very slowly. So if I do like going 1,000, log of 1,000 is 3. It is log in base 10, you know. And if I go like even bigger, I don't know if log of 1,000,000 is 6. So it is growing very, very slowly. And practically you can say that, I don't think log ever passes a certain limit. So you can actually, you know, put a imaginary line that the function will never pass. And you will say that is my asymptote, so that this function is bounded. Bounded means that like there is this limit that the function value never passes. But this is not true for logarithm. Logarithm will pass any value. Let's say I want to pass this line right there. There's a better way of doing that line, so I'll do that. I can create a different function. Let's say like y equals 5. Yeah, maybe 5 is too small. Let's say y equals 100. So, and I will zoom in. So as you see, that's my asymptote. It's a constant line, and it doesn't pass there, but it actually does. X to the power of 100, actually y equals 100 line. And I know that because like I can solve the logarithm equation. And since log x passes a certain value, log of log x will pass as well. But log of log x will even grow much, much, much smaller. And by like slower, I mean very, very slow. Just to get a comparison, if you look to the 1,000,000, log x is smaller than 1. And for this function to equal 1, you need x to equal 10 to the power of 10. And 10 to the power of 10 is a very big number. Um, to make a comparison, like this function is less than 2 for 10 to the 70. So let's say x equals 10 to the 70. This function is less than 2 because 10 to the 100 makes 2. And number of atoms in the universe is around like 10 to the 75, 10 to 78. So like even for number of atoms in the universe, this function is still smaller than 2. But this function is not bounded. So there is no constant limit that this function is always slower from. And I think that's a very good analogy. That's an analogy, by the way. Like that's not the exact formula of ZK snarks or anything, but that's a very good analogy of understanding succinctness. Succinctness doesn't mean being constant. So it's not constant, it's not bounded, and there's no certain limit. But for any practical reason, you can assume it to be constant because my computation will never grow enough so that the computation itself passes a certain limitation. Does it make sense still here? Okay, great. And a second important point, so two important points. One is that that's not bounded, this is not constant, very important. Second, it doesn't need to be small. This is a very misunderstanding. When we say that something is constant or succinct or compact or like any of these small words, people think of a small number. This doesn't need to be necessarily true. A function can be very big, but still constant. For instance, a very simple example. This time I will draw myself. So let's say this is my graph, and I will use white. So let's say I have this function and this is constant, or like this is not constant, but you know, this is polylogarithmic. So it never, like it grows very, 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 very slowly. It grows even slower and slower each day. So it's very slow. And this function seems also small. It is growing small, slowly, and it is also small. Why? Because like here our value is 100 and we say 100 is small. But let's say I multiply this exact function with like 1 billion. Then this function becomes something like that. Now our function is not small. It's actually very big. And maybe my actual computation is this. So for a very, very, very long time, my computation is actually smaller than. So my computation itself is faster than the function's growth speed. So being succinct doesn't imply being small. It just means that after a certain point, you will be smaller than a linear function. So if one of the functions is linear, a linear function is, you know, x, and one of the functions is like logarithmic, log x doesn't need to be smaller than x. If log x has a very big coefficient, then up to a very big x, it can actually be bigger than the linear function itself. That's why thinking ZK proofs as efficient or as small doesn't make too much sense. And until very, very recently, and when I say very recently, it's like 10, 15 years maybe, verifying ZK proofs were really expensive and we didn't do it. Verifying ZK proofs were succinct. Like SNARKs are a very old concept. SNARKs are not new. But even though SNARKs existed, they weren't efficient. SNARKs don't need to be succinct only. They also need to be efficient. Does this make sense? So I see a question on the chat. Fractals, like Mandelbrot, kind of bounded functions. Yeah, fractions are not functions to start with. Like they are not functions, at least on the xy, because like they actually map multiple values to the same x. So like it depends on your norm, and I'm not sure. Probably, but yes, probably they are not because I'm not sure. But like, it's not important. You can think of simpler functions, you don't need to go 2D. Just think of, what is a bounded function? For instance, 1 over x plus 1 is bounded. This function will never ever pass, sorry, 1 over x plus 1 is bounded. This function will ever never pass 1, basically, it starts from 1 and it's always like going slower and slower, and it is bounded between 0 and 1. It can never pass 1, it can never be slower than 0. You can just play around with functions, just type in bounded functions, and this site is amazing. As I said, just look to functions here. It's very cool. We can, for instance, look to the previous function I said. Sorry, x plus 1. Let's actually go to the more logical domains. So by the way, x is between 0 and 1, so we don't assume negative x values. So as you can see, it's 1 here and it never actually be 0. It can never pass the line. So for instance. Okay, so that was being succinct. I think that was a good understanding of like why, being succinct is important. And I just said that like, okay, before this part, I want to mention something else. I just said that like until very recently, SNARKs weren't efficient enough. This was 2 reasons. So once you create a proof, there are some metrics that you want to know about. What are some metrics of proofs? Let's write them down. So for instance, the proof size. Proof size is the like size of the proof that I have for some certain computation. It's in kilobytes, megabytes, I don't know. 1 second for the question, sorry. So important stuff for proofs. So one is proof size. This is the verification time. One is generation time. One is generation memory complexity. It can be something, etc., etc. So these are important stuffs for proofs. And when we say something is succinct, we say that the proof size and verification time are succinct. Something can be succinct in verification time and not succinct in proof size, or vice versa. But we usually mean both. So just as a small note. Yes, Hatun.
I get the idea of bounded, but I didn't understand the succinctness. Like, are we saying bounded functions are succinct?
No, succinct functions are growing very slowly. They are like, in mathematics, we say
not bounded.
polylogarithmic.
But they're
They are
not
not bounded. They are like logarithm.
okay.
Logarithm is a very good example of a succinct function. It is growing very slowly and like it's not bounded.
So succinct means a function that grows really, really slowly.
Yes. And this function is over proof size and verification time.
Okay.
So these two are the things that are growing very slowly. And in respect to what? In respect to the proofs computation complexity. So you can think this as number of gates in the circuit. You can think like number of assertions we make in the proof, what the proof is proving to be correct. You can think more abstract as well. All these are correct. Okay.
Yep. Thank
Any
you.
other question? So, okay. These are the important stuff for proofs. And I just said that something being succinct is not something being efficient. And until very recently, we didn't use ZK because of 2 reasons. One is like we don't need that much privacy applications. One we will discuss more in detail later, so I'll pass one. Second, ZK wasn't efficient. Verifying something by just repeating computation was much more efficient. let's say that you want to prove someone that like you have 100, bank transfers, and all these bank transfers checksum makes like, I don't know, $100,000. You want to prove this to someone. The other party repeating the computation is much, much, much faster than you generating a proof and then them verifying. Because like even if their verification is slightly more efficient, it is slightly more efficient, and what you do is very, very much more expensive. So like it doesn't make the effort. But with blockchain, that changed. Because in blockchain, we have like blockchain is basically a replicated state machine. And this implies that we repeat the computation to make it trustless. Once you send a computation to Ethereum, that computation is repeated 4,000 times for each single validator. That is why ZK rollups make sense. Because we need to repeat the computation so many times. That is why in blockchain, ZK has a so meaningful use case. Because in ZK, we have a lot of verifiers. In real life, an information is verified once or twice or three times. You don't verify an information 5,000 times. Let's say I wanna buy a car and I want the other party to prove me something. They give me some document and I verify it for once because I am the party buying and they are the party selling. So I only need to verify it once. But if I'm doing this exact same thing on blockchain, it is verified on each single validator. And also by every client that is downloading, etc. So that's also something. But in the end, verification on blockchain is much harder because there are so many parties verifying the same information. That is why being succinct is important. Because being succinct, basically, there's a limit that after that, it will make sense to actually have a proof to verify some information instead of just repeating the computation. Is it clear? Yes, please.
I'm sorry. What do you mean by repeating computation?
So what do we prove in proofs? Let's say I have this function fx equals y. I want to make a proof of this. What does the proof say? The proof basically says that I have the function f. I run it with x, and the result was y. This is what a proof says to be correct. If it's a ZK proof, I don't see x, I just see assertions. But like, let's forget about ZK property because not all proofs are ZK, and ZK is important only for privacy, and zero knowledge is much bigger than privacy. Snarks are much bigger than privacy, let me say like that. Or something can be only a snark. Like we say ZK snark. There are also snarks that don't have privacy. So, this is what the zero knowledge proof says. And if I verify the proof, I learn what? Verification tells me that fx was y. And what is a much simpler way of learning fx was y? Just running the function f. That is proving by repetition. So like always the simplest way of verifying something is just repeating the computation. So by definition, if a verification is more expensive than repeating the computation, then the verification is like does not worth the effort. So.
All right, thank you.
But that wasn't the case, by the way. Verification is always more efficient, but verification is not more efficient with a certain, like, let's say that, okay, I will draw you something. I think it will be much more clear. Let's say I have a prover and a verifier. I said that there are two scenarios. So in one scenario, prover uses 10 seconds to compute the result, and I use the exact same 10 seconds to verify their computation. That is verification by repetition. So I repeat the computation. In the second scenario, prover doesn't need 10 seconds. They need like 10,000 seconds because they generate a ZK proof, and generating a ZK proof is expensive. And verifier needs like 9.9 seconds to verify. So this doesn't make too much sense. The verifier gained like 0.1 seconds and prover lost like 9,990 seconds. So it doesn't make sense. But let's say I have 1 million verifiers and only one prover. Then that makes sense. And in blockchain, that is the case. In blockchain, we have a lot of verifiers. Like in Ethereum's case, all validators need to verify. So we have 5,000 verifiers. Maybe I should. Sorry. We have 5,000 validators. And there's only one prover because there's only one rollup generator. So the prover size is always one. So it makes sense. Even like a small improvement in the verification cost worth the efforts. There's also something called aggregation, which we will talk about like in a minute. But even without aggregation, zero knowledge proofs are important because they have this motto, prove once, verify all everywhere, and as many times as you like. So, okay. So I continue. That is succinct. And remember, we were talking about ZK snarks. So we learned like ZK snarks are ZK. They are succinct. They are non-interactive. So I sent the proof once and you can verify as many times as you like. That's also why we have this motto, prove once, verify all. And like fourth, their argument of knowledge, they are proofs. So that we already knew. Um, hmm. Yes, okay, I'm reading the question from chat, sorry. So first question is, what is the domain of a definition of the function? A function is succinct over a domain, right? So yeah, like there our function is basically a circuit. So I guess you can think that like it should be defined over a field and it should be like linear, etc. So like there are those, but we are computer scientists here. And in terms of the like way of looking of the computer science, all functions that we have on computer science that we code can be created to be a ZK proof. And the succinct property is true for snarks. And snarks are Turing complete. So whatever you can do with a Turing machine, you can actually generate a snark for. Um, so like that's not a problem. Um, is there a metric to know how many verifications a proof had? Like, no, because I can verify like on my local, no one learns that I verified something. Yeah, it makes more sense in blockchain because in blockchain the computation is more expensive. Because so even a small improvement in the computation costs is a huge improvement because computation is so expensive. Like think like that. Let's say you're increasing a number's value by one. So you have a counter and you're increasing your counter by one. You have this number x, you are doing x plus one, Doing this in your computer, it's like one gate, literally one computation. You're increasing x value by one. Doing this on Ethereum is like at least 5,000 computation because each validator needs to do. And then they need to update their state. So they need to generate Merkle witnesses for their state. And Merkle witness is like 250 operations because it's on a Merkle map. It's a Merkle tree on Ethereum's case. So I'm not sure I don't know for like Merkle tree. But basically, for only incrementing x by one, you do like 50,000 operations or something on Ethereum instead of one. So it is very less, like very more inefficient. I don't know. Okay, I passed this part. I think it will become clearer as we go along. So I will come to other parts. So this was ZK snarks. And you will hear some rumors about other properties of ZK snarks that they have or they don't have. This is not true. ZK snarks can have any of these, or maybe they don't have. They don't need to have. Being snark does not imply the existence or the non-existence of any of the things here. First of all, absence of a trusted setup. People will say you that snarks need a trusted setup or the other way around. Snarks don't need a trusted setup. Both are wrong. In like old snark setup systems, there was a trusted setup. Trusted setup, I won't explain what a trusted setup, but we don't like a trusted setup. So like having trusted setup is something that is bad. And like previously snarks had, but like I guess 10 years ago or something, like we had snark proofs that didn't require trusted setup and new schemes they don't have. So, that's all information. People will say you other proof types can be more or less efficient and snarks should be efficient to generate or not efficient to generate. This is not true either. Like snarks can be very efficient to generate or can be very less efficient to generate. Like snarks don't tell you anything about proof generation efficiency or proof. They just say that the verification will stay succinct. So they don't tell you any information about generation. The snark keyword, I mean. Post-quantum security, that's also a common misknowledge. People will say that snarks are not post-quantum secure. There are post-quantum secure snark schemes. And yeah, like it doesn't really depend on your proof scheme. It depends on how you get zero knowledge or like soundness. And you can have informational theoretical soundness on snarks, which is post-quantum secure, etc. So it's possible. And finally, recursion or aggregation. We will explain what these two are, but snarks can have recursion or they cannot have recursion. Like both is okay. Having recursion or not having recursion isn't a reason to be or not to be a snark. This is important to understand. Trusted setup is not necessary. Yes. We don't need trusted setup for snarks. Snarks, they don't define having a trusted setup. You can check online to see like which was the first snark to not have a trusted setup, etc. But yeah, we have a lot of them right now. So this is like, no. It was like that before. So that's why. Okay, so I continue. I will pass to a second chapter, which is really important in terms of using ZK snarks. So until here, we explained what are ZK snarks and what are their properties are, or what are not their properties. Now we will pass to a concept that is quite important, which is recursion and aggregation, which is very important to understand because we use these two a lot. So this is the diagram that I did, which I believe explains perfectly. In the left, we have aggregation, and in the right, we have recursion. Aggregation is basically that you create a ZK proof that verifies two other proofs. So I have the proof 1, I have the proof 2, and you verify these two proofs inside another proof. I just said that proofs are Turing complete. So you can do whatever you do on a computer on a proof. Thus, verifying a proof is something that you do on a computer. Thus, you can verify a proof in a proof. But this is not true for all proof schemes, by the way. Like not all proof schemes have this, or more appropriately, have this in an efficient manner. For some proof schemes, aggregating proofs is like insanely expensive. But in some new schemes, it's not. And you can aggregate proofs very efficiently. So let's say I have a proof that verifies I am older than 18 years old, and I have a proof that verifying I am a male. I can combine these proofs, aggregate them, and I will have a proof that verifies I am more than 18 years old and I'm a male. So that's an aggregate proof. And a recursion proof is that you, again, verify proofs inside another, but you verify always the same proof. There's a base proof, and then you always verify the exact same proof each time. So like a good example is blocks of a blockchain. Each block is a proof of same type. Like they don't have the same inputs. Inputs they change, but their verification key stays the same because the assertions that the proofs do are not different. Thus, if you verify a proof inside another proof, that becomes recursion because you always recurse the same proof. So these are not two different proofs. That's why I use the same color in recursion, but there are two different colors here. Color coded. Never miss. So yes, that is the idea. And by the way, a small information, maybe you didn't hear that before. Identity of a proof. So once I say like these two proofs are different, that is the verification key of a proof. And the verification key are the assertions in a proof. Inputs, they don't change the verification key of a proof, and that makes sense. Like inputs should not change the identity of a proof. Yes, Almas.
Yeah, Yunus, can you please again explain the concept of recursion? I didn't got exactly what's the process. Why? Because the color coding scheme here you mentioned proof one, proof two are two different proofs. But while recursing again, why it is the same proof one only? Can you please shed some light?
So when I say the same proof, I mean that assertions and the computation is the same. So let me define a ZK proof that takes like X as input. And the proof will do two things. First, it will assert that X is less than 100. And second, it will output X plus 1. Okay, that's a proof. I can recurse this proof inside each other. What is recursing the proof? I add another argument here. I say, ZKP is the first argument. I verify, and I don't get X as the argument. I verify ZKP. And then I like set X equals ZKP.output. And then I assert this and output this one. And then I just call ZKP over itself over and over again, just like a recursive function. And this basically allows me to like use the same proof to verify itself. This is not the same as aggregation because in aggregation, the input that you get is not the same type of me. In here, input is the same type as ours. So that's why it works.
Fair enough, Yunus. Yeah,
So,
thanks for the question.
Of course. In computer science, that is composition and recursion. So aggregation is composition, recursion is recursion. No, the name. And probably you don't like, it doesn't make too much sense to you right now. But in very old languages, composite types were possible, but recursive types didn't exist. So, you created this class, and the class, uh, like it had the right to have fields of like other classes, but it wouldn't have a field of itself. So it wasn't possible to create this class of student that has a field, it's also student of type. So recursive type definition wasn't possible, but composite types were possible. So it's a bit the same. Aggregation and recursion are different in that sense. How many times I do this recursion? I can do as many times as I like. There is no limit. That is the most beautiful part. We said that ZK proofs are succinct. Ooh. And what happens if a ZK proof verifies itself? The verification becomes cheaper and cheaper. So you can actually combine as many proofs as you like to verify as efficiently as you like. So that is the most beautiful things about ZK proofs. I said that a ZK proof is logical to create after a certain input size. So if your input is so small and if your computation is very fast, then you can just repeat the computation to verify. Let's say I have this function and it just, outputs x plus 1. If I want to make sure that x resulted in the correct way, I can just add 1 to x. But I say that I have 1 billion f functions for 1 million different f values. That would take 1 billion operations on my side. But with ZK, I can create a proof for each functions and then I can aggregate them all. So that I have a proof that is again verified in as short time as before. Maybe it was a long time, but it's the same time for 1 billion functions. So that makes it that point it makes sense. It is like rollups. If you have a rollup that only has one transaction per block, it is stupid. You can just send the transaction to the chain. So a rollup should have more transactions than L1 so that the rollup is efficient. Does it make sense? Everyone understood or? Okay, there's something on chat. How do I measure efficiency? Time, for instance. As I said, ZK proofs are succinct, so they are practically constant. What does it mean practically constant? So let's say, I have these proofs and all ZK proofs are verified in like more than 20 seconds. For a proof to be verified more than 30 seconds, since it is succinct, it is like, logarithmic, you need the proof size to be like a billion times bigger. So basically all proofs are verified in less than 30 seconds, we can say, because that big of a proof is not possible. So verification is always constant, most of the case. It's practical constant. It's not constant. It can go infinity. It can take infinite time to verify a proof because it's not constant, but it is growing so slowly that it is practically constant. It's just like log x. And the first question, okay, I explained that one. Aggregation, recursion. Aggregation is verifying two different types of proof. Recursion is verifying yourself. It's recursive functions over like aggregate functions. Okay, any more questions here? Does it make sense, the concept of aggregation and recursion? And now the picture looks much better, right? Okay, I have two different proofs. It verifies them. I have the same proof verifying itself over and over again. Okay. Then we will pass to applications. So this was the concept of snarks. I explained you all the important things about snarks. We discussed being succinct. You know what is succinct right now. We explained it's not bounded, it's not constant, but in practice, it is constant. It doesn't pass a certain threshold because like input size that cannot change the verification that much. So that's why, in practice, it is constant. That's why we usually say that they are verified in constant time or, constant size, etc. One thing. Second, we said that nothing here is required to be a snark or, not like is required to not be a snark, etc. So basically nothing here is a common property of snarks. That's very important to understand. We didn't discuss the first parameter, trust setups. I don't think that is a subject of this course, so I'll pass that one. We discussed about efficiency in proof generation. So basically that is the time that it takes to generate the proof or the memory it takes to generate the proof, etc. Snarks, they don't need to be efficient. They don't need to be not efficient. They can have anything. Post-quantum security, we said that snarks can be post-quantum secure. And finally, we said that snarks can have efficient recursion or aggregation. All proofs, if they are Turing complete, they can perform recursion and aggregation, because recursion and aggregation is just some computation. And if a proof can do any computation, it can verify itself as well. Here, recursion and aggregation, once we say that they are available in a proof scheme, we mean that they are efficient to do. They are not like billions of operations. So that's in practice, they are possible. That is very computer scientist of ours. Once we say that something exists, we actually try meaning that it is, very efficient to do, or, at least somehow efficient to do. If something is very, very expensive, we just say that it's not possible, because we don't do it. Okay. Now I want to explain in my less like 5 to 10 minutes, some applications for snarks. So as you know, ZK snarks have the property of ZK. So the first big bubble that we create using ZK is privacy applications. And I want to talk about this because privacy applications, or ZK, are very misunderstood. Guys, ZK is not encryption. It's not encrypted computation. It doesn't give you privacy. It gives you like a very special type of privacy, but it's not possible to do what you do with like encryption using ZK. And using private applications with ZK is like something that's very complex, and basically you can't do everything. For instance, I will give you like some very common misunderstandings. First of all, private voting. People say to you that like you can make a private voting application with ZK and votes will be private. No. With ZK, it's impossible for you to make votes private. You can make voters private. Without using an encryption scheme like FHE, or I don't know, regular encryption also, okay, you can hide votes. It's not possible. You can hide voters. There's a huge difference between these two. So you can hide that I am voting, but you can't not hide what I am voting for. For instance, that is the example with voting. Or with payment. Private payments are not possible with ZK. You can't implement a private payment protocol with ZK. You can implement a protocol that has public deposit cash is. Tornado Cash is not a private payment protocol. It's a public deposit, private withdrawal protocol. Your withdrawal is private. Today, we don't have enough time to talk about all ZK applications and how these look like. I just say these so that you know. I don't like talk rubbish. Basically, these are true, what I'm saying here. So if you have another opinion, we can discuss later, like in some other time. I'm just trying to give you some understanding of like why ZK is useful and why it is not. And it's not possible to do all privacy applications with ZK. ZK is for something very, very, very specific. There are some questions I see. Yes, we can hide who is changing the state, but we cannot hide the state change. Yeah, that's a very, very good summary. Exactly. For instance, private state is not possible. It's just private updates that possible, with public commitments. You can also, by the way, have, state committed in a public manner. That's also possible. Basically, instead of having the entire state, I just have, the Merkle root of the state, etc. So that's a commitment, if that makes sense. That's also possible to do. The case is proof and trust. Privacy is worth not. Yes, we have a proof of that information. And with a proof of that information, you cannot build all type applications. Private messaging is also another like great case. If you want to hide messages from rest of the community, you need encryption. You can't do this with ZK. ZK does not hide anything. ZK hides the input while public outputs are there. So you can have public assertions on private input. But if the input is private, it's private to everyone. If you want to make something, shared information over a public channel or something, you need encryption. ZK email as well. That's a good example. In ZK email, we don't like hide our email. We basically hide our private key, so that it's like no one knows our like password, for instance, to access emails. But everyone sees that there's no ZK by the way. So ZK email is not a privacy use case, I don't think. Maybe ZK email is not the great example. It's more like in ZK email, we verify the computation was done, but it's a public computation already. So it's a public communication. So it's a public proof there. We don't need private inputs for ZK email. So yeah, that's the case. So this is very important to understand. Then you might ask, then like, why do we use ZK for privacy applications? This is not cool. I thought, ZK was the next generation privacy. ZK is next generation privacy because they have an advantage. Ooh, ZK snarks are usually, in parentheses, have information theoretical security or privacy, not cryptographical. What does it mean? In encryption, you hide an information by having a secret key. And this is like this, since the beginning of time. And probably this won't change. Like with post-quantum cryptography, etc., encryption methods, they get better and better. But there is always a secret out there that we are hiding. And if some party has the secret, they can decrypt our output so that they learn the information. So nothing is secure. Right now, we don't have like quantum computers. That's why, our Zoom meeting here is right now secure. But Zoom can just, store these encrypted meetings on their database and decrypt later once there's a quantum computer. Or, we say FHE is post-quantum, latex-based cryptography. Guys, at some point, latex-based cryptography will be broken. Like we are certain that it will be broken because it's just a hard problem and all hard problems will be solved eventually. I'm not sure about that, by the way, but I think it's possible to broke it. Like there's a probably third, so I'm not sure. But in that, it's very possible that it will be broken. So if you are cryptographically making something private, you will lose the privacy at some point. But in ZK proofs, it is information theoretically private. The proof does not contain your information. It doesn't hide it. It doesn't contain it. But very important. Once you hide an information, the information is out there. We just cannot access it. In ZK proofs, the information does not exist. No one can touch the information because it's not inside the proof. So that's why snarks are information theoretically secure. By the way, this is true for privacy, not soundness. There are also information theoretically sound ZK snark schemes, but I think there are, but like they are very rare. But for privacy, this is almost always true. Yeah, I think so as well. Yes, hash is a good example. Hash isn't a perfect example because you can always get the pre-image, etc. But yeah, hash is a very good example. Even if you get an input from the hash, you don't know if the input was real. And if the input was just a secret key, you getting the input from the hash doesn't tell you anything. Because by looking at the input, you don't know if it is the right input or it's just another pre-image of that hash. And if you need that exact input, then it doesn't tell you anything. And for instance, in the ZK vote case, you can actually hide voters until the end of time. No one will ever know where the voters are, for instance. Okay, I have a fun question below. So I thought it was fun. I don't know. So it asks, let's say I have a recursive snark. Can it have cryptographically secure ZK, but not information theoretically? So basically, let's say I have this theory that I say a recursive snark should always be information theoretically private. Am I right? So thinking about this, I think that can be a very advanced question, but I will leave it here. Like, if anyone wants to answer this, I don't know, you can reach to me after the session so that we discuss this. That's the question that I came up with, so I'm not sure if it is academic, but I think it's impossible to have the other way around because it's succinct. So basically, the information that's contained is always going to zero. So that's why it's interesting. We have a comment on the chat, but I didn't understand. Maybe some more information would be nice. And yeah, that was about the privacy part of ZK snarks. Any questions about privacy? Okay. And again, like if you want to discuss about this question, you can just reach out to me later. And finally, we have scalability applications. Snarks are very useful for scalability because they are succinct. And again, they are useful to use because they become smaller and smaller, not smaller and smaller. They like their growth becomes slower and slower as the input goes to bigger. So there is always a point that enough input will make the verification of a proof very efficient. So the verification's time complexity will be, verification's total time will be much less than repeating the computation itself. There's always a point. That's why rollups, etc., they make a lot of sense. Because with ZK, you basically can verify as many information as you like at once. You get all the transactions happening on, you will listen from Starknet in a bit, or there's Scroll, it's a ZK rollup as well. You get all their transactions. You create a single proof for all their transactions and you verify it. And they are succinct. Thus, the verification costs like always the same amount of money or time. It's expensive, by the way. Like I know that Scroll's verification takes like, I don't know, $5,000 or $15,000 per day. So that's very expensive, guys. But if they have enough transactions inside the proof, that's worth the efforts because it's constant. They always pay $5,000. They don't pay, if the transaction count is less than 100, it's 5,000. If it's less than 1,000, it becomes 60. No, it's always $5,000. That's why it makes sense. No information should be concerned that they are not quantum resistant. Yes, we should be concerned because their soundness can be broken. So let's say I have a privacy protocol using ZK. Quantum computers cannot be an attack vector against my ZK proof. It can just be an attack vector for the soundness. So yes and no. Let's say you have a rollup. You don't need to worry for the old information you have settled so far. But if Google has a quantum computer, then yes, you need to change your proving scheme so that they cannot create unsound proofs. Soundness means that like the proof generated correctly. And if you have a quantum computer, you can create a proof that's not correct, but you cannot decrypt the information. By the way, this is not a snark common property. That is a possible snark property, and it's usually true, but not common. Snark just means success again. Of course. So we also have other use cases, but I think I am a bit over my time. So there are P2P applications for ZK. That is nice. And there are also Lightning Network sorts. That's also very useful and logical to do with snarks. But yeah, that final note is really important. ZK can never, ever, ever solve double spend problem. That's why we need blockchains. ZK can achieve trustlessness. It cannot achieve censorship resistant. It cannot solve double spend. There is no mathematical formal theory proving that, at least not that I have seen any, but I think it's very easy to prove. So yeah, ZK can never, ever, ever solve double spend. And yeah, that was my presentation. I hope it was useful.
It was really good.
Okay, thank you guys.
Thank you. It was so useful.
Of course.
If you have any questions, Yunus also in our Telegram group so that you
Exactly.
can text him and yeah.
Yeah, I shared my Telegram and Twitter, etc. before. Again, this was a very long introduction, I know. And I know there are a lot of properties there. You don't, the slides. Oh, yeah, I can send the slides. My Telegram is by Görlek. So yeah, basically the most important point to understand is that ZK is a very useful technology, and there's a reason why we work on ZK so hard, so much. ZK is useful, ZK is logical. But there's also another important point. ZK is not like what you think it is. So that's why if you want to use ZK, you need to understand ZK very well. You cannot just add ZK to any application and it becomes private. ZK doesn't work like that. Or it's the same for scalability. ZK doesn't make everything scale. You can use ZK to scale something very efficiently, but it's not always the case. And that's my conclusion.
Thank you.
Thank you guys again. And I need to run. I have something to do beforehand. So, and I hope like Ganana, you have an amazing presentation and I hope it was helpful. Yes.
We will continue with Gyan and
Bye.
Yunus, take care.
Bye, everyone.
Bye.
Thank you so much. Bye-bye.
Welcome, Gyan. Now we're gonna continue with Starks, and we have
Okay.
an amazing tutor. So yeah, floor is yours.
So I know that the previous session was like a bit much, so I'll try to cover different things related to stacks in just like maybe half an hour. I prepared a presentation for 45 minutes to an hour, but I think it'll be way too overwhelming. And then you'll just forget everything and just bunch stuff up together. So I'll try to just cover like an umbrella of what stacks are, just the thought process behind how stacks were created. And what I'll do is I'll just put some key instances here and there that will either make you curious to explore Stacks and StackNet, or you just end up having a lot of questions, either or which is a good scenario, right, in a learning journey. So I'll start with a small, let me just share my screen. I have absolutely missed every mathematical component that is associated with this because I think stacks are extremely complicated just to understand from a mathematical standpoint, right? And that's why I try to condense as much information as possible into this. And also, my role has changed quite a bit. I'm working a lot with startups now that are working on StackNet. So a lot of this that I'm doing is from muscle memory that I've already done. I also did prepare a document for questionnaires and then just some intro and stuff that I'll share in the chat. So if you have any questions, don't hesitate to put them over there. It could be just about anything, just from like zero knowledge proofs to StackNet or whatnot. And I'm happy to answer them or get them answered in case it's, too complex and I just don't have the answers. Okay. So I'll quickly run through what is proving, how does it work. It seems to me that most of this has been covered in the last previous sessions, right? So I just wanted to add this so there is some context to like what is happening. And then we'll go to Stark proofs, what is Cairo, and then how does actually Starks get proved in Ethereum? And then how can you think about proving them elsewhere in any other environment, right? So quick context about proving. Right, so this is a process in which a prover wishes to execute a computation and convince a verifier that the result is correct, right? And as Yunus mentioned in his previous talk, non-interactive proving is what is the most important element in everything, right? So Snarks kind of introduce that, so that's why you have the scalable non-interactive argument of knowledge, and then with Starks you have slightly one more addition. Oh, sorry, Snarks you have succinct, and we are scalable. So scalable transparent arguments of knowledge, right? So the S and T are slightly different. We have scalable in our system because we have created something that will help you scale the proofs. Instead of doing individual proofs for every single scenario, we have created something that will help you generate proofs in the most common way possible. So that's why you have the scalability part, and that's why StarkNet and Stark proofs were created to make sure that proofs can scale. And then you have the transparency element, which is, the non-interactive element exists, but with Starks, the aim was to make it more transparent. So that's why it is, Starks. And that's what I'll be talking about. So here the verifier doesn't actually have to execute the program, but is able to know that the computation is happening correctly. So that's what is proving all about. And how does it happen? All of these other elements are actually the how part of what proving is. So the first step that you go through is called arithmetization, and that is why we were talking a lot about when succinctness, there is, log x, the polynomial and all of that, because when you're dealing with all of these proof systems, what you're essentially dealing with at the underlying is polynomials, right? So you take a computational problem and you need to convert it into an algebraic form. So a lot of times you might come across this keyword called AIR, which is algebraic intermediate representation. It is something that is used in Stark proofs as well, but generally used in a lot of proving systems, which means that you need to have some sort of intermediate representation in an algebraic manner, right? Which is what you sort of take and perform the mathematical operations on top of, and then you're able to do all of this non-interactive kind of proving. So you take the computational problem that is given to you, you convert it into an algebraic form, right? And this algebraic form is actually essentially representing your program operations, the logical steps, and all of that. These are being represented as polynomials over finite fields. We are not going to go through anything about finite fields and all of that, but this is you will find this in abstract algebra. Not very interesting, but if you read it like 3-4 times, you will eventually get it, right? And then what we are doing is we are capturing a behavior of a program, right? Mathematically, that's all we are doing. And initially, when we generate that, let's say we call it the expected polynomial, right? That we expect a particular program to work a certain way. Once the program goes through this a sequence of states or steps, right? So that is your execution trace. Execution trace is actually something common that you would find even in other programming languages. So any program that you write, right? At the underlying, it is actually going to a hardware, and then it is being steps of that program are actually being stored in a register, right? So you see register values. This particular register is currently, some hexadecimal value 0x00. So if you have actually tried to break a program and see inside of it, you would have seen some of these things. And then if you have studied computer science, then there is also the hardware part of it that you will, digital science, where you understand how registers work and how values keep moving from one register to another, things like that, right? So the execution trace is like a log of every instruction executed, right? The register values, the memory accesses, etc. at each step. So this execution trace is also turned into a polynomial. So this is, let's say this is your execution polynomial, right? So you have your initial problem statement, you have an expected polynomial, and then you have your execution trace that your program actually goes through, and let's call it the execution polynomial, right? On top of this, what happens is there is, so any correct run of this expected program will generate an execution trace that all fall on this expected polynomial, right? So the way you are checking whether the expected polynomial is actually similar to your execution polynomial is by checking if the points that we mentioned, like this is a polynomial, so the polynomial will go through different points in the graph. So you're actually checking that all of these points actually do they fall on the expected polynomial. So the prover has to convince the verifier that all points of the execution trace fall on the expected polynomial. But how do you do that without checking all of these points, right? So there are going to be like lots of points that are going to be part of this polynomial, right? Imagine a polynomial going through your entire sort of graph, right? There are going to be so many points in this. So what you do is, the answer is you end up checking some random points, right? As a verifier, I'll end up checking some random points. And that is called your error correcting codes, right? All of these are, by the way, just your straightforward concepts that you can find in communications and, digital computation and all of that. So ECC, which is a set of techniques, when you actually use to transmit data in telecommunication, it allows you to detect and correct errors, right? In this context, we don't need to correct errors, because what we want to prove is that as a verifier, I just want to randomly check some points, right? Which is that non-interactive part. And I want to make sure that, okay, these random points are falling on the polynomial. So I'm happy that, what they said the program will do, the program is actually doing that. So this prover is able to prove this statement to me, right? So what this ECC does is, it will, if there are errors, it detects these errors and it amplifies these errors, right? So that is why if you make a mistake, even if you make the smallest mistake, right? In telling that I will do this, but you're actually not doing that, then that small mistake will flare up, right? And that is the job of ECCs, which is, to the smallest mistake, it will highlight and it will sort of, so that the end result is you are able to check randomly whether the execution polynomial and the expected polynomial are the same, right? And this helps the verifier to not have to retrieve and analyze the ECC output, because the ECC will tell you where the mistakes are, like it will highlight the errors, right? And the verifier will sample a few parts and check for errors, right? So this is a kind of summary. I think you were already familiar that this was happening, but I just wanted to share all of this with you, so you know what is the exact process like of actual proving that happens. Irrespective of Stark proofs or Snark proofs, some of these things are common, right? Like you have the arithmetization, you have the execution trace and different things happening. Just the way the proofs are generated, just the arithmetization part will be different, right? And then probably the way the execution trace is generated. So the execution trace is nothing but a matrix. Sorry for the disturbance. The execution trace is nothing but like it's like a matrix, right? So you have all of these instructions and stuff, and just the format of the way these things are generated is different because of the underlying, let's say, mathematical elements that we are choosing to do these things. Like sometimes we may use a particular type of function, right? Like one of the examples was log x as one of the functions, right? I don't really know if snarks, what function snarks are using, but you could use an elliptic curve, right? You could use an elliptic curve function to do. So the polynomial function that you choose will differ from proof to proof, largely because of the way those proofs function and things like that. But this is like just the overall context of how you are able to successfully do a prover verifier thing, right? With this, let's try to understand how Stark proofs work. This is always a fun slide. So the creator of Stark proofs is Eli Van Sassoon. He is currently the CEO of Starkware. And yeah, and pretty cool, really amazing research that went behind all of Stark proofs, right? And the idea is simple, right? From a mathematical perspective, if you look at it, if I had a 1 million degree polynomial, and if I could prove to you that I know 1 million values of x where it goes to 0, right? So that's like your logic, like, but you wouldn't have to calculate the polynomial and on each of the 1 million points, right? So basically what you're saying is the probability percentage of me being able to check that this using random values, for example, as a verifier, me will use some random values and check whether what your statement is true or not, right? And the probability of that, the truth being really high and me as a verifier being convinced is possible with Stark proofs, right? And this, of course, the whole point is to save time. So this was the basis of like the way the Stark proofs kind of came together. They are a family of cryptographic proof systems that can be used for privacy and scalability. I don't want to emphasize too much on privacy, which is ironic because this session is about CK and privacy. But as Eunice mentioned rightly, doing privacy related stuff on especially on Starknet, which is where a lot of Stark proofs currently are being generated, verified on Ethereum at the moment. It is very, very difficult, right? And a lot of times, like he mentioned, privacy is an exaggerated concept. In terms of people don't really understand what are the things that can be private and that cannot be private, especially in this case because Starknet in itself is a public blockchain, right? Which is built on the concept of Stark proofs and such. And when you have a public blockchain, then, and saying that you will have privacy, you will be able to easily build privacy focused stuff around that is not very, it's sort of, contradictory, right? Because a public blockchain is meant to have data which is extremely public. But scalability, yes. So as Yunus mentioned in his presentation as well, right? You can have scenarios where you can use ZK proofs to scale. And this is one of the scenarios where you can use Stark proofs to scale your operations, right? And that's why Starknet is its biggest strength is being a roll-up, right? So being a ZK roll-up that rolls up transactions to Ethereum and gets a bunch of transactions verified in one shot using the computation proofs. So what does it do is that Stark proof statement saying that a computation was executed correctly. That's what it does to Ethereum, right? You do a bunch of transactions, you bundle them together, you send them to Ethereum and you say that all of these transactions were done correctly. And think of all of these transactions come together as, a polynomial. And you sort of, as Ethereum as a verifier is trying to verify randomly by checking a few transactions or, just for an analogy, that whether some of these are correct or not. And even if there is a small mistake, your ECC will kind of blow that up. And then, verifier is satisfied with a higher probability that yes, these proofs make sense and we move forward, right? So some of these simple statements that you can think of is like the 1000th number in Fibonacci sequence is X, right? And then I have signed 100 bank transactions I have 100 signed bank transactions that are valid. So things like this, right? Just some sort of computation. And the verification time for this. So the main thing about ZK proofs having strength in being rollups is that the verification time is exponentially smaller than naive computation. If the verification time to verify a bunch of proofs is larger, then this whole scalability thing just, falls on its own. So why does it matter? I think all of this already familiar that, we have distributed computing. We move from being able to do on centralized servers to advocating for decentralization. So the way blockchains do help decentralize value transfers, computational proof helps prove that code execution was correct, right? So you do things, even though things are naturally happening with integrity, right? So you're doing the right thing even when no one is watching. That's the whole concept of blockchain, right? And that's what computational proofs do to code execution. So this has also been covered, but I want to emphasize that with Starks, one of the major reasons that Starks were created was to make sure that the blockchains become more and more scalable. We started the Stark ZK proofs with blockchain, of course, because there is a kind of application that works here. But there is also more that you can do, especially as it becomes better and better. You can work with ZK proofs on doing a lot of scalable stuff, right? You can also have privacy elements, but it will be slightly more complex than it is right now, it seems like, right? Okay. So now we have seen a bit of context. We have seen what are Stark proofs. The next question is how, right? So ZK snarks, you write circuits, right, to prove. So what you end up doing is that you end up writing for every kind of proof scenario, you will end up writing a circuit for that, right? So you will be writing your circuit in some circuit-based programming language. You will feed that circuit, and your circuit is very specific to a particular problem statement, right? And the how for Stark proofs is a little bit more different, right? So with Stark proofs, we went one step ahead and created something called as Cairo. Now, Cairo and Stark proofs are very closely related, because what we wanted to do was we wanted to make sure that this provable computation can be done in a scalable format, right? So for example, in this scenario where you have to rely on Stark proofs for provable computation, that means your code has to be expressed in the form of polynomials, right? So finding the right polynomial for a program is a time consuming, it requires specific skills. So this is exactly what you're doing when you're writing those circuits for snarks. You're actually trying to find the right kind of logic. So you write a specific circuit for a specific program, right? That's what you're doing. You're trying to actually find a polynomial that fits. But here what we did was we instead created something which is more for flexibility, right? Like how you can execute any kind of computations on CPUs, right? Whereas you build ASICs, which are for specific like application specific designs, right? So application specific, so that's what ASICs are, that they are very, very application specific, and they are very hard to design, similar to how you design your circuits, right? So they are not general purpose circuits. Whereas CPUs are more general purpose, right? They're cheaper, they're vastly available, and they're easy to program for. And you can have a single, architecture for multiple purposes. So here you have efficiency versus flexibility, and we have moved more towards flexibility. So just quickly, I will quickly go through this, like what this would look like. So if you would have to build a stack manually, just like you build an ASIC, right? You will have to design the trace in terms of figuring out how the trace would look like. As I mentioned, the trace is nothing but the trace needs to be represented in the form of a matrix. So you see, this is like your sort of matrix, So you have to design how many columns will be there. How would you what would each cell mean, right? And then you have to add constraints onto this. There is a lot of manual optimization how much trace space can you have, and then what will be the prover time, what would be the memory, and things like that, right? So this can get very complex very fast. And if you try doing this parallelly in Snarks as well, you can see that as you try to build circuits for more and more complex problems, the circuits themselves become very, very complex, right? Because at the end of the day, the circuits will have a lot of simple things like NOT gates, they will have AND gates, they will have simple gates that you're actually just putting together as a circuit, right? And when you're doing a complex logic, this can become very complex, very quick. And after that, you would need to have you would need to create the right kind of tools. So these are like your physical tools, right? So you will have some FPGAs, for example, how you use that gate arrays for performing logic things and all of that, right? So in this case, what you would be doing is that you would have to try to make general purpose algebraic intermediate representations that can be connected to other algebraic intermediate representations. So like all of this just says that, oh, this is like going to get complex over a period of time. And then you need a programming language as well for these things, right? And all of this is like, until step 3, it's a very complex life. And this is where Cairo comes into picture. Cairo actually is nothing but CPU AIR 0, right? And that is shortened to Cairo. And all of this I have already explained to give you context. So CPU for your, like your general purpose, for all of general purpose computations. AIR is your, algebraic intermediate representation, and 0 stands for the first, like the 0th AIR, kind of like a common one, right? So you have one AIR, one verifier, right? So what you're going to do is you're going to build, we have built a common AIR or a common implementation, which is like one common circuit. Think about this as a common circuit, which will be able to prove any logic that is sent to this circuit, right? So that is the biggest, if somewhat anything distinguishable from other proof systems is this, that one of the most complex things about writing these or using these proof systems is writing the circuit logic itself. And what Starkware early on has done very beautifully is to create this general purpose programming language where you feel like you're just writing a program, you're just you just have to write a logic, and internally that program translates into a general purpose circuit that is able to create Stark proofs for you. And that's the power of like why Stark proofs there are lots of other things, like I think Yunus also mentioned like post quantum security that we talk about, that Stark proofs are by default post quantum secure, they are more efficient and proof size and all of that. But for me, feels like this is one of the biggest standouts, being able to have a general purpose programming language that can actually create proofs for you right off the bat. Very interesting, very different, and somewhat, I would say, extremely innovative, right? And it takes a lot to a general purpose circuit, right? And that is what Cairo is for, right? It stands for CPU AIR 0. It's a universal machine, Turing complete, and you actually pay for only what actually ran. So you pay for the amount of computation and stuff, and you can build as complex as a logic into this, right? And yeah, so there's some like comparisons and stuff of efficiency. But this is the most interesting thing, right? So Cairo is a high-level language. It is very similar to Rust, and it compiles to something called as safe intermediate representation. All of these steps now, I think you have some more context why this is happening, is because you have to create algebraic representations. You have to make sure that the language compiles into, this general purpose polynomial that you can actually test, right? So that's why Cairo program compiles into a safe intermediate representation called Sierra. And then, even if a program fails, there is a proof that is generated, and that proof is invalid. So invalid proof is generated. So you are able to know that this program failed. And the sequencers are always compensated, is fine. So this Cairo program generates a safe intermediate representation, then it generates a Cairo assembly, which then creates a validity proof. So we don't call them ZK proofs because they're actually not zero knowledge. They're not completely zero knowledge, right? But they are, you can validate whether something happened the way it was supposed to happen. Your completely zero knowledge requires you to have hidden parameters, which is that one piece which is missing. And I mentioned that's also because Starknet is a public blockchain, right? So instead of ZK proofs, we call them validity proofs.
Kian, we have
Okay.
a question in.
There are questions. Sorry. Okay.
and
I'm gonna.
also, yeah.
The matrix is for the coefficients of the polynomial or for something else. Circuit is your choice of polynomial. I would say the circuit itself is more like, are you asking in this case specifically for Starknet? Because for Starks, we don't have to write the circuits. For Starks, this is like, there is like a general purpose polynomial that they have chosen, and Cairo builds on top of that general purpose polynomial. So that general purpose polynomial is able to validate as many scenarios as possible. So maximum number of scenarios, you can generate a proof using that general purpose polynomial. So in this case, we don't actually have to write the circuit, but we have chosen that or built that general purpose polynomial in that way. So for star, that is the truth. For the matrix is for the coefficients of the polynomial. This I'm not so sure. I have an example of how the matrix is generated. I will try to find that, and I will share it with you. There is some
Yeah, my,
information goes into the matrix, but I don't really know if it is the exact polynomial coefficient or if it is something else.
Oh yeah, it was just related to the step one that you mentioned, that we have to choose the coefficients of the matrix. So you mentioned 4 steps, and I was asking about the step one.
Oh, the first, which is the arithmetization, right?
Yes, and you talk about the
Oh,
matrix
here?
at that point.
Oh, here, right? Assigning
Yes.
a one. Yeah, I think it is, but I'm not 100% sure. I will check, and I will tell you. I have a sample matrix itself for Stark proof mathematics, so I'll check in that and I can share with you.
Okay, thanks. And you mentioned the generic polynomial. What's its expression?
I don't have it. I'll share that with you. It's all of this I have in that mathematics part, which I have
Okay,
completed.
sorry. All right,
No,
thank you.
no worries. But if you could, can you put your questions on the doc that I shared? So I'll make sure to answer all your questions, even if I don't have the answer right now. Or I can copy paste it later as well. No worries. Yeah, so basically I want to summarize by saying that Cairo is a high-level language which is inspired by Rust.
Again.
And
I'm so sorry.
sorry.
Again, I think Almas also has a question.
Okay, yeah, let's go.
Sorry.
Yeah, just wanted to confirm whether sequencer is equal to a validator, or those are two different aspects of
No, I have a diagram for that, what a sequencer is. But sequencer is something that produces blocks. I will shortly share an architecture diagram as well that will help make it clear.
works. Yeah, thanks.
Okay, nice. So yeah, this is like a simple summary. All you have to do using Cairo is that you just need to write the logic without having to worry about the math behind it, and it all happens in the background. That's why also I'm not that worried. Okay, so now the last section that I wanted to cover was how do you prove Starks on Ethereum? This is very simple, very straightforward. And this is where I think some of that architecture diagram will come into picture. A lot of this presentation is very tightly coupled with Starknet, right? And you would see this not because Starknet is the only entity that uses Starks, by the way. There are also other folks in the ecosystem that are using Stark proofs themselves. But this is very closely tied to Starknet because right now Starknet is that platform which is producing maximum number of Stark proofs, right? In the most efficient way possible. So for me to draw any parallels, it makes sense to talk about how Starknet works in collaboration with Ethereum. Otherwise, it is very difficult for me to explain. I didn't want to keep this presentation very tightly coupled, but if I don't do this, I have no other option but to go only into the mathematics of Stark proofs, which is very extremely complex. Okay. So so when you think about like when you're proving something, right, on other blockchains, for example, Snarks and stuff, like I mentioned, you have to generate your circuit for that particular problem statement. And then you write a verifier contract and then you send the proof to that contract and it kind of verifies for you, right? So in this context, the verifier contract, let's say, is deployed on Ethereum, and then you generate a circuit wherever, right? So you generate your proof on client side and all of that. I don't know if any of you all have had any hands-on workshops with Snarks, but you can generate a Snark proof client side. You can generate the proof, send it to a Solidity contract, verifier contract, which is deployed on Ethereum, and it will verify the proof for you. But in this case, you don't have to generate a circuit, like I already mentioned, because you just need to write your Cairo program and it will transpile into the Sierra. And do you need to write a verifier contract? No, because we already have deployed contracts on Ethereum, verifier contracts on Ethereum. And you also actually don't even need to send the proof to Ethereum. All of this is already being done by Starknet, right? And what Starknet is actually, it is, so the only circuit that you need or the only program that you need is to write a Cairo program, right? Its verifier is already written, deployed, and audited on Ethereum. And the Cairo language will compile to these instructions executable by the CPU. And correct execution of program will generate a proof understandable by the verifier. So what you do is when you write logic and you write your logic in Cairo program, right? You deploy your Cairo contract on Starknet. It will generate the proofs for you, send it to Ethereum, and the Ethereum's verifier contract, which is already deployed on it, verifies that proof and says, okay, good to go. So there's one circuit to rule them all. This is what I mentioned by a general purpose circuit, right? So how does this happen? Your Starknet in itself is a Cairo program. So you deploying and executing a smart contract on Starknet is actually a part of a bigger Starknet workload, right? So we have this prover called Sharp, which I will talk about. And Sharp is the one which is constantly generating Stark proofs and sending it to it sends it to Ethereum, and the verifier on Ethereum verifies these proofs, right? So any Cairo program that you deploy is actually part of Starknet's workload itself. And this workload is sort of, part of a bigger proof. So the recursive proofs that he had shown, Yunus had shown in his image earlier is what goes here, right? So you take a proof, you send it, and then you again recurse over multiple proofs, and then you send the final sort of smaller trace kind of thing to Ethereum. So this is where this is somewhat significant in talking about the other things. I won't spend too much time on this, but the way it works is you send your whatever transactions happen on Starknet, right? You have the Starknet OS, which is your sequencer. Sequencer is an element which will take the transactions and then make them into blocks, right? Which is what Ethereum does for you. And one of the things that is happening right now in Starknet is that we are trying to decentralize this sequencer, right? Right now, we are running the Starknet sequencer, but we are slowly moving toward decentralizing. We had a recent update that had this ability to. So now, when will decentralization happen? When anyone is able to take and run the Starknet OS themselves, right? So there are lots of different OSs, and then it's decentralized. You send the transactions, it is picked up by one of the sequencers, you create a block. From there, you get this execution trace, right, which we mentioned earlier, which will go to the prover called Sharp. So you get the program. So this is where you get the whole, looping of the proofs. You take the execution trace, you send it to the prover. The prover generates the proofs and sends it to verifier. So here is where you can see the two different entities. You see one entity, which is the proof generation entity. Think of this as just proofs being generated anywhere, right? In Snark case, you will be able to generate client-side proofs, maybe on your system or something, right? And in case of Starks, you have the sequencer, that is, we have the prover itself called Shard, which is generating the proofs. Sorry. Okay. So there are some other elements as well to this, which you don't really need to know right now, because then it becomes a little bit more in-depth stuff. But this is what this Stark proofs. This is how they are being generated at the moment at a large scale. Okay. Okay. This is fine. So Sharp is the shared prover. So SHARP. What it does is it aggregates Cairo jobs, and that is how the cost of verification for each job is becomes very less. Otherwise, imagine us as Starknet. Right now we are bearing the cost of generating all the proofs, right? But the only way we can reduce the cost is by having recurring proofs. So the jobs can be Starknet blocks. We also have another service called StarkX. So workloads from there, or any other arbitrary Cairo programs that you decide to generate proofs on your machine, let's say, right? And you want to send it to Sharp directly, you can do that as well. We recently released this so Sharp is one of the provers that has been battle tested for a few years now, but we recently released a very fast prover called Stu, right? And it is open source. It is a staff prover designed for client-side proof generation on real-world devices. So if you want to generate proofs on laptops, you want to generate proofs on mobile and all of that, Stu is like your go-to prover. And there's recent benchmarks that it has outperformed the established ZK VMs, like RISC-0 and all of that. SP1 also, there is some figures around that. And this is built on an interesting protocol called CircleStark. So all of these are just enhancement of your Stark proofs protocol. And here they use the Mersenne Primefield M31. I won't go too deep into it, but because of this, we have certain performance gains in Stu, which are unavailable in existing Stark constructions like Sharp. We also had another one, Stone Prover, right? So this is like the new prover, and this Stu prover is actually very interesting because not just Starknet, but there are a lot of other ecosystems as well that are interested in kind of experimenting and playing around with it. In the doc that I shared, I've shared some documentation around this, so that might be good to read. And so I showed you in the previous architecture diagram. So this fact registry has got to do with Ethereum. That how does Ethereum know that bunch of these transactions have been verified? That is where your fact registry comes into picture, right? It updates these information that is coming from the proof systems. If the proofs are valid, then they are saved in the fact registry. So that's how Ethereum knows that something was executed. So when we say this is a layer 2, that is how we use the layer 1, where the layer 1 knows that, yes, X amount of things happen on layer 2, and I have the proof of that. And the Starknet OS, or the sequencer, is also a Cairo program that describes the blockchain network and what constitutes a valid state transition. So when transactions come to this sequencer, it has to make blocks out of it, right? So that this OS itself will determine whether a particular state transition is valid or not. And running this allows you to run the network and generate a proof you did. So like I mentioned recently, we have sort of expanded on this whole decentralized sequencer stuff. So very interesting things that are coming up. And the Starknet OS smart contracts will query the fact registry for the tuple in case it wants, let's say, what happens if the sequencer crashes, or there is an issue here. That's where your fact registry comes into as a backup, where you query and see, okay, whether these transactions happen successfully or not. Yeah. So, and then you kind of, loop back into updating the latest state of Starknet. So the way proof systems work on Starknet is that smart contract execution is included in a Starknet job. And this is included in the prover. and the sharp itself runs off chain. So you can actually run your own prover, right? But they are sent to Ethereum to verify. And the verification generates facts on chain that can be used by any smart contracts. And the state of Starknet is managed by this. So when something goes down, you can pick back the state of Starknet from here. How many times does the Starknet verifier verifies one proof? Starknet verifier will not verify the proof. The verifier lies on Ethereum. So it will, Ethereum verifier verifies the proof. I believe it only verifies it once. So so it is as simple as just sending a proof to your Solidity smart contract, right? And the smart contract will verify that whether this proof is valid or not, right? And it will just add it to the fact registry if it is valid. If you are saying how many times does this action happen, how often does this happen? I believe that might be, is that the question, intended question? Like how many proofs go within a minute or something? Does Starknet have a testnet to learn Cairo and test in all the Starknet stack? Yes. Yes, we have a testnet. It's called Sepolia. But if you want to play around with mainnet as well, it's super cheap, so you can also do that. But yeah, that's actually all I had for today. If you are interested, I can show you some. So I wanted to show this image. I don't know if this is seen, but it's a very interesting thing about execution trace and how they work. Let me also share this on the sharing is past, it seems. It's very fun. I think Carolina, because you have more security experience, I think you will enjoy this. This is like how you explore the execution trace analysis and stuff in that context. I also shared some stuff over here. Some hello world example to start. Yes, I will add that actually. This is a hello world example. I will add that in the doc. So the interesting thing about Starknet is that you can also actually verify snark proofs on Starknet. It is super interesting and super somewhat out of my current depth of expertise. But there is a lot of interesting stuff happening on this where you can basically verify Noir ZK proofs on Starknet. So there is an SDK so there's an SDK that's released called Garaga that can do that for you. So you can actually verify snark proofs on Starknet. Very interesting stuff, right? So you can actually, so what this means is that you can use Cairo to also verify a snark proof, or I would assume that Cairo is some sort of general purpose circuit that you take a snark proof, which is a specialized circuit. You build a proof of that and then verify that. It's very interesting. I don't really know how more about the technical elements behind this because I haven't worked with Noir so much. But basically, when you can you compile your Noir code using Garaga, and it will automatically produce a Noir prover and a Noir verifier contract written in Cairo. And now that your both prover and verifier contracts are written in Cairo, you can actually, immediately deploy this on Starknet. What this means is you sort of, you can move this proof verification to Starknet. The whole thing about, I think the whole idea of this is to have significantly lower transaction fees and faster processing. That's it. There is really, apart from this, from an advantage perspective, there is nothing much to it. You can make your on-chain life much easier as compared to having to pay hefty amount of fees and waiting for a certain amount of time and things like that. Right now it is very fast also because the sequencer is centralized, right? But when it becomes more and more decentralized, of course it will become little bit slow, but ideally not not as much, because the amount of transactions that you'll be verifying also will be a bunch, right? Instead of verifying one after the other. So these are like, I feel, certain really good advantages when it comes to like rollups, validity rollups. But from a privacy context, I didn't add anything much because, like I mentioned, it's very hard to do privacy stuff on a public blockchain like Starknet. And you can do things like using this, Garaga SDK, and you generate snark proofs. In this case, they have given Noir as an example, but you can pretty much generate snark in any even like robust or the most basic circuit language, right? And then use that to verify that on Stark. So there in your snark proof itself, you might be able to add some level of privacy, right? Right, while writing the circuit, you can hide certain parameters and such. But other than that, the moment you go on a public blockchain, that state change is almost immediately visible, right? So you will have to hide it right at your proof level and things like that. And then you have no control once it goes on a public blockchain. So your parameters are anyway visible. That's why we don't also encourage people building that much privacy stuff. Like I think one example that Yunus showed that is happening right now on Starknet is these mixers, right? You are able to deposit publicly, but you can withdraw privately, right? So there is some level of privacy that you can ensure, but it's not too much. And even to do this is like super complex. You can't do that easily. So this is, I think, one of the use cases that people are working on. We have a project called Typhoon that is building this privacy mixer. But other than that, anything else like all of this private voting and stuff like that, Starks doing privacy with Starks is very, very difficult. Very, very difficult. Even mathematically very difficult. So if you do want to build something privacy related and you still want to leverage Starknet for the lower fees and faster processing fees, shorter processing time, then I suggest to go the Garaga route, which is you take Garaga SDK, you generate your. See, at the end of the day, anyway, you're going to generate proof on client side if you want it to be private, right? So you can generate client side proofs and then send it to, use one of these SDKs, send it to Starknet. It'll be quick and cheap for you. So you have to do the privacy elements yourself. Other than that, I don't see any other significant privacy related stuff. But interesting tech you should definitely explore. And if you have any questions, feel free to keep adding on to the doc. Just at any point in time, also, if you have any questions, like even just like really basic stuff, how does this work? How does that work? Or if you get stuck somewhere, just add that doc. I'll make sure to keep looking at it frequently and make sure to respond. I'll add some examples that you can explore and stuff. So yeah, super cool.
Perfect.
Uh,
Thank you, Gyan. It was
ecosystem.
amazing.
Yeah, okay. I think tried to finish it in 30 minutes because I have a habit of speaking more.
No,
Taken 40
no.
minutes.
Floor is yours, and we love to hear you. So, do we have any other questions that, since Gyan is here, you want to ask?
Yeah. Is it because staff proofs are interactive that the verifier verifies only once? This is a good question. So the Stark proofs, the thing is there are ways to do interactive Stark proofs and there are ways to do non-interactive Stark proofs as well. But because this is so my understanding is this, right? That because this is a general purpose circuit, you don't need to verify it multiple times. Like when you are verifying a specific circuit, then you are trying to make sure that it is giving you that certain output. Like you're saying x plus y is equal to 5, right? So you're trying to do like x equal to 2, y equal to 3, and then x equal to 2, 3, and y equal to 2. So you're trying to put as many things as possible to get convinced with 100% that, okay, like this person is saying x plus y is equal to 5. But this works if you are running a specific circuit. But in a general purpose circuit, my feeling is this, that general purpose circuit is optimized to verify, and even the verification that will happen, even though the contract verifies once, I think that once verification itself will have x number of random input, because any verification essentially means that you are satisfied with higher probability and higher randomness that this is successful, like this is valid. What you're saying is valid. So even though operationally the verification happens once, I think that once itself will include this whole process of doing it multiple times. This is what is my thought, and I'm not 100% sure about this, but I feel like this would be the process even in snarks. Like when you're doing non-interactive, even though you're verifying multiple number of inputs for randomness, that whole thing is captured in just one block of code, which is we are calling it verify once. Like even if you do a snark circuit, deploy it on a solidity verifier, you just run the verification once. So that I would assume that it generates random points and does it in one block. It's my thought, but I'll share. Yeah. Oh, there is more questions. Learning this is difficult. What advice do you give us to help? I would say just build apps. Like it has been, for me, it has been one of the most useful ways to learn, right? Even if you're building a small app, Hello World app, like, just start somewhere small and don't go too deep into the mathematics of it, right? Like, I'll tell you honestly, I've been in the Starknet ecosystem for 3 years, and even to date, I can't explain Stark proofs properly, okay? I think sometimes I feel like none of my teammates have that confidence, but because I'm a woman, I feel even less confident, right? And I feel the only person who can talk about Stark proofs with 100% confidence is Ellie, okay? So it is okay. You don't, but that doesn't mean like I'm not confident of building on Starknet, or I'm not confident of advising other people to build on Starknet. In fact, I built that profile over years. So don't be scared to start because you feel it is complex. Start with things that are small and ask questions. Ask a lot of questions. I feel like this is one of the things people lack a lot. And earlier, I have also seen like I and if you just feel like you have a safe space to ask questions, that's it. Ask, even if it's very basic, like very small, or you don't understand even how Hello World program is working, it's fine. Just ask questions. I think this is the best thing, right? And it's okay. Some days you'll find it hard, but just gotta push through and just you'll come be better on the other side for sure.
Are there any questions? I think
Awesome.
not. Thank you for your time, and it was amazing. And if you have any other questions, you can use our Telegram group, and it's make everything more interactive. We can also join the conversation. And thank
Yep.
you very much again. Like, I appreciate
Awesome.
it.
Thanks for having me. Yeah, thanks everyone. Yeah.
And
Have
yeah,
a good one.
bye bye. Take care, all of you.
Yeah. Thanks.
Bye bye.
Bye. Thanks.